In this video, we'll focus on modeling secondary steel beams in ideCAD Structural. You'll learn how to use the secondary steel beam command and adjust key settings such as alignment, offset values, and placement configuration. We'll also cover how to assign connection types that comply with capacity design principles, ensuring safe and code-based modeling. Next, we'll explore shear stud settings and how they affect composite action between steel beams and slabs. Finally, you'll learn how to access and override critical design parameters, including deflection limits and stiffness-related checks. By the end of this video, you'll be equipped to model secondary steel framing systems with structural accuracy and confidence. Now, it's time to model the secondary steel beams. I go to the secondary steel beam command under the Steel tab and click once. In the opened window, you'll see the beam commands again. You can select the section from the drop-down menu. IPE 240 is already selected. Let's also check the settings on the far right. Let's start with the General tab. This tab allows you to configure how the secondary steel beams will appear in the perspective view, including color and material. Under the Structural tab, you can select any section from the drop-down list containing sections already loaded into the project. If you click Load Section, you can also access all available European and American profiles. You can also select a section directly from the list, or simply type the name of the desired section using your keyboard. For example, I typed CHIPE 240 and pressed Enter. The Castellated beam section is now visible in the preview. Below that, you can see the steel material. If you'd like to use a different material, use this parameter box to change it. Below it is the rotation option, which cycles through 0, 90, 180, and 270 degrees. Since I'm using a castellated beam section, I want to ensure joint safety at both ends by entering a value of 1 for the number of solid segments at the beginning and end. This ensures that the connections form with the proper geometry. Moving on to the Placement tab, Placement Type, there are two modeling methods available. Count-based, you enter the number of secondary steel beams, and the software calculates the spacing. Interval-based, by default, this is set to 120 centimeters. I'll change it to 150 centimeters. By the way, if you right-click inside the box, you can switch units. I've now set it to 150 centimeters. Once the modeling is complete, the software will automatically calculate the required number of secondary steel beams. For example, with 150 centimeters spacing, it might generate 3 beams depending on the span. Even if the input box is inactive, the calculated spacing will still be displayed. If the span isn't evenly divisible by 150 centimeters, you can activate the extra element input box. You can also activate or deactivate checkboxes to adjust the placement of the first and last beams to avoid any overlap. At the bottom, you'll see the Offset menu. You can specify how the beams are placed relative to the reference elements. Perpendicular to the first element. Perpendicular to the second element. Free offset. I'll leave both X and Y offsets set to 0 for now. In the Extension tab, under Orientation, you'll see 3 options. Over top. Top-oriented. Middle-oriented. Since we want compatibility with slabs, top-oriented is currently selected. If needed, you can enter a custom delta value for vertical positioning. Below Orientation menu, there's a Connection Type drop-down menu. Clicking the arrow reveals several predefined connections, such as single plate, double angle, single angle, T-plate, etc. You can use any of them for modeling. I'll select the T-plate for now. Elements created using the secondary steel beam command are automatically connected to the main beams using the selected connection type, ensuring that all corresponding connections are modeled simultaneously. It's important to note that all of these connections are predefined in the software, designed in accordance with capacity design principles. What does this mean? The geometry and dimensions, such as plate thickness, width, and height, bolt diameter, bolt count, and distances between bolts and to the edges, are all configured to comply with relevant design codes. The software pre-designed the connection according to the moment and shear capacity of the associated beam section. So, because these default connections are already capacity compliant, the design is automatically safe. If you want to reduce the capacity manually, you can later adjust it through the Connections menu. Under Extension menu, if you're modeling cantilevers, you can enter lengths for both the right and left sides using the respective fields. In the Intersection menu, the Division option defines how much trimming should be applied at the intersection between consecutive secondary beams and the main beam, preventing any overlapping. When I go to the Shear Stud tab, just like in the main steel beam command, you'll see three options. Don't add studs. Automatic stud placement. Always add studs. I'll leave it on automatic stud placement. After we model the slab, if it's defined as a composite slab, the software will automatically determine the stud configuration and use those values for design. We'll dive deeper into the stud parameters when we look at the slab command, so I'll skip it for now. Under the Design tab, just like with steel beams, you can adjust LTB, unbraced length, and CB parameters. The software calculates them automatically, and you can also review the values in the Design menu. If you ever need to manually intervene, these fields are available. For example, I typed 1.5 here just to demonstrate. I'll leave it passive for now, but you can activate the field and input the value when needed. Below that, you'll see the deflection limit, by default set to L/240. This value can vary depending on the design code. You might also want to override it for special cases. This is a setting shared with the main steel beam command. However, for special beam types like cantilevers, if a different deflection limit applies, the software won't change the value automatically. You'll need to make the adjustment manually. For example, for a cantilever beam, you might need to change the value to L/150. So, if a beam has a unique structural role, like a roof beam or cantilever, be sure to adjust the deflection limit manually under the Design section. I clicked OK. Now, back on the plan view, you'll see the placement arrows. I clicked to select the beam. On the perspective view, you can also see a green arrow on the selected beam. Then I selected the final beam on the same axis line. The modeling is complete. Let's zoom in a bit to get a better view. If we want to check for clashes, we can see that there's no overlap. The interval-based setting is 150 centimeters, and the software calculated the count as 3. We didn't need to enter this manually. Now, if I disable these arrow options, you'll see that the secondary beams at the beginning and end of the main beam clash with each other. To resolve this, you can either apply an offset or choose not to model those beams. I chose not to model them. With 150 centimeters spacing, the secondary beams aligned perfectly with the 6-meter span. I clicked OK and exited, and now we're ready to use the slab command. Thanks for watching. Don't forget to like, subscribe, and explore the knowledge base for more tips. See you in the following video.